Capacitors are components that can store electrical energy for a short amount of time. Because they can quickly store and release energy, they are very important in many electronic devices. Capacitors are used for different purposes, such as storing energy, filtering signals, and helping circuits work more smoothly. When a capacitor is connected in a circuit, it goes through a process of charging and discharging. In a simple RC circuit, which contains a resistor and a capacitor connected to a power source, the capacitor charges very fast at the beginning and then slows down as it gets closer to its maximum charge. The behavior of this process is described by the time constant, which is calculated by multiplying the resistance by the capacitance. The time constant represents how quickly the capacitor charges, reaching about 63% of its maximum voltage in one time constant. On this lab, we will study this process.
Okay, so the materials we used in this lab are not one, not two, not three, not four, but these extra two wires, and then we used the Pasco 850 universal interface, and then here we used the Pasco RLC circuit, maximum working voltage 10 volts, that has one 10 ohm resistor, one 33 ohm resistor, one 100 ohm resistor, a light bulb, another light bulb, 150 ohm resistor, 100 microfarad capacitor, and a 330 microcapacitor. And we're gonna use this computer to see the graphs.
So today we're going to be doing lab 6, and we're going to be doing some graphs to figure out the RC. And the first thing that we're going to do to set up is connect the wiring to the capstone and to the RC. So first, we have the battery, essentially, that's connected to the capstone, and that's going to go, the black one is going to go on whichever one of these batteries you want, and we're going to do 330. And then the red side of it is going to go over here at the top. And then for these separate ones, we also have an extra loose one that we are going to be using to cause a jump. And for the red one, the one that's connected to the output of it, of the capstone, the red one is going to go to one of your resistors. And since we have the option to do 133 and 10, we're going to be doing 10. And then with the black one, this one also goes with and then for this extra one that's going to be causing the jump, it's going to go at the top of your resistor and at the top. And that's it. So now, since we already have our capstone already set up, so we changed the signal generator. So now our current limit for amps is supposed to be 1.10. Our voltage limit is 10. Our amp is 5, and then our frequency is 1. And we have our auto clicked off. And then we also have over here at the bottom, we have our voltage current sensor, and it's set to 500 hertz. So the first thing that we're supposed to do for our experiment is, now that we have our RC circuit already set up, we're going to click record. Okay, so we got that, and now that we've gathered this, we're only really interested in one of these humps. So what we're gonna do is zoom into it so we can get a more accurate reading. And the values that we need to collect are the values when voltage equals 0. So it needs to be the time where voltage equals 0, and it's supposed to be like right before we get into the actual curve. So here we already have 0.07, so we know we're not supposed to use this one. So this is the time that we're supposed to use, and the second time that we're supposed to use is 63% of your voltage. So that's going to be when your voltage is 3.15. So we're gonna try to get a more accurate description. See if we can get to 3.16.
You sum up both of them.
So this is probably
Using the bigger ones, you're using
the closest that we're gonna get to, I think.
the second
But
experiment.
so for 3.10, we can see that it's 0.504, and then we'll go more into our data analysis of how we're gonna use these values. But these are the values we're going to use: 0.498 seconds and 0.504 seconds.
Now, what we're gonna do is we're gonna connect the two capacitors in parallel. So looking at this, I'm gonna connect this end with this end. Boom. They are
Similar to our first RC circuit, we did the parallel as we explained before. We just added the extra wire. So we're gonna do the same thing in running our graph, and we should get a similar graph. Similar to our previous RC circuit, the only thing we did was add an extra wire to make them parallel. So similar to our first experiment, we're going to be running our graph again. And as we can see, you should be getting somewhat the same. And like I said before, we only really care about the 63%, which is going to be 3.15, and we can get that with our little indicator. And we're gonna try to get as close as we can. It might be easier if we keep zooming in.
Wait, in the black screen?
Yeah.
Yes. So.
Oh, is that what you were telling me right now?
Yeah.
And then we do the 3.15. Oh, it's
So for this lab, we used two tables. We used one table for one capacitor and a second table for both of them in parallel. So this is what the values came out to be. For the first one, we have the time when it was 0 and the time when it was 63%. Their difference, the experimental capacitance, the theoretical capacitance, which is what is on the board we were using. And from this, we were able to calculate the percent error, which was 81%. On the second table, we have that it took 0.494 seconds, and to reach 63%, it took 0.505 seconds. We have the difference in these, the experimental value that we calculated from these values, and then we have the theoretical capacitance, which is both of the capacitors summed up since we used both of them in parallel, and we have the percent error, which was 155%.
what is causing the percent error? So it's human error. That's what's causing the percent error. And how can we modify the setup to have better results? Maybe we can have more digits after the decimal to get like a more precise answer. What are all the time constants similar? Should the time constants be different? Bro, hold up. What is this question, bro?
Overall, for conclusioning this experiment, we observe how the capacitor charges and it discharges in a circuit. We also measured the times constant and found that it was close to the expected values. And we realized that all the errors and the difference in percent errors were likely due to human measurement errors or even component tolerances. And overall, we confirmed that the time constant really depends on the resistance and the capacitance.
Hi, I'm Gabriela, and I did the data analysis.
¿Habla?
es que no me dijiste que ya. Hi, my name is Gabby, and I did all of the procedure.
Hi, my name is Emily, and I did the introduction.
My name is Alan, and I did the materials and the process.
Hi, I'm Itzel. I will do the conclusion then, and then I'll edit the video.